Welcome to Session 7 in our series on electricity and magnetism. In this session, we're going to explore how the Earth's magnetic field protects us from the high-energy charged particles coming out of the sun. We're going to start with reviewing what we learned in Session 6, where we explored how charged particles behave in a magnetic field. Specifically, we're working with electrons. So let's take a look at the device we used in Session 6. And what we have here are two coils of magnet wire which produce a relatively uniform magnetic field where this little glass bulb is. And we're going to produce a beam of electrons, and then you'll see how they behave in a magnetic field depending on the directions that they're moving. So I'm going to, we're going to need to turn the lights down a little bit. And I will also rotate this. And let's turn some lights off. And then we're ready to go here. And there's the beam. Now, there's no magnetic field on yet. As we energize the magnetic field, you'll see that the beam will bend into a circle. And let's take a look at why it's doing that. This is something we learned about earlier. This is the Lorentz force. It's our second left-hand rule. And the blue represents the direction of the magnetic field, which currently is into the globe. The red finger indicates the direction of the electrons when they first come out of the electron gun, and then the finger in black represents the force that's the electrons experience. So when they first come out of the gun, they are deflected upward. As they change direction, the direction of the force changes, and this continues all the way around, and that's why we get the circle. Now, if the electrons are going parallel to the magnetic field, either in the same direction or totally opposite, vectorially speaking, then you just get a straight line. However, if they come in at an angle, we get a combination of the translation and circular motion, which is a spiral. Okay, so that's the behavior of charged particles, whether they're electrons or protons or other charged particles. They will exhibit this kind of combination of translation and circular motion. So let's take a look at the problem that the Earth's magnetic field solves for us. Here's a conceptual drawing of something called the solar wind. It's emphasized by these lines shooting out into space. I say conceptual because, as you can see, it is not to scale. And it doesn't capture the complex Sun-Earth magnetic entanglement. If it were to scale, that is, if this were the actual size of the Sun we were going to use, the size of the Earth should have half the diameter, and it would be about 100 Sun diameters away. It'd be very difficult to show all of what's happening here with that kind of a drawing. So we're going to use this as our concept drawing. The Sun produces two types of radiation. The familiar electromagnetic radiation we call infrared visible light, ultraviolet, and then there's wavelengths greater and lesser than the three that I mentioned. What we are concerned with here is the less familiar particulate radiation that the sun ejects out into space in all directions. These high-energy charged particles, electrons, protons, and alpha particles, which are basically helium nuclei, are generated by powerful electromagnetic activity within the sun and not from the thermal activity at the sun's surface. If these high-energy charged particles were to reach the surface of the Earth, two bad things could happen. One, they could damage our cell structure. They have enough energy to break the bonds, our chemical bonds that make up our bodies. In fact, if it weren't for the Earth's magnetic field, life never would have evolved on Earth. The other problem is, as these high-energy particles come into our atmosphere and they strike the atoms that are in our atmosphere, they can knock them out into space. Over time, they would sweep away our atmosphere. So neither of those two things are a good thing. But our Earth has a magnetic field around it that protects us. Let's take a closer look at how particles behave when they encounter it. So these lines represent the Earth's magnetic field, and as these charged particles come shooting at us from the sun, the magnetic field either deflects or captures those particles. So these particles cannot come straight in and strike the Earth along here. We're protected. But something looks dangerous up here at the poles, because it looks like these spirals just continue until they strike the Earth, both in the northern hemisphere and over here at the South Pole. But really, things are more complicated than that, fortunately. Notice how the magnetic field here at the poles is so much more concentrated, and they're kind of coming in at these angles. Let's take a closer look at how that change in magnetic field from out here to this concentrated sort of field affects the charged particles from the sun. Here we have a single charged particle and a single magnetic line of force. So notice that as the spirals approach the highly concentrated magnetic field area, the spirals get tighter and tighter and tighter until they reach something called a mirror point, where they reverse direction and then go back around. They may do this several times until they either strike each other in their spirals, or they strike the particles that are sitting out here in free space. Certainly this is not atmosphere, but there are particles here. If they strike each other and go off careening out into space, then we're okay. Or if they give up their energy, they are no longer of any consequence regarding our health. Some of these particles get very deep into our atmosphere, where they excite the electrons of our atmospheric atoms to a higher energy level. When they drop back down to a ground state, a particular wavelength of light, in other words color, is emitted. The color depends on the element and the energy level of the particle. It results in familiar auroras. The aurora borealis in the north and the aurora australis in the south. And then here is a view of an aurora from space. Now, I want to spend a little time talking about how this process is really occurring. What is making that happen? I told you that it's the intensity of the magnetic field, but I'd like to kind of spend a little time on that with you. I want to dwell on what causes that reflection. And the reason is, not only is it important for what we just talked about, protecting the poles from being inundated with the high energy charged particles, but that principle is also used in trying to harness nuclear fusion using a magnetic bottle. So we're going to start with the Lorentz force. I have this sheet representing a parallel uniform magnetic field. We've already seen what happens with that. If we have the magnetic field, as shown here, parallel and uniform, and an electron is running parallel to that magnetic field, it continues to just move unaffected, no deflection. If it comes in perpendicular, we end up with a circular motion. And if it's at an angle, because we have a perpendicular component and a parallel component, we get the combination, which is a spiral. So far, so good. Now, what if we have a magnetic field that starts out parallel like this, and it becomes more and more concentrated? So there's sort of a funneling effect here. Let's take a look at what happens. So we start out again, out here with the uniform field. We're just doing this and the electron's moving along. As it enters this region, notice that as the magnetic field is turned, the force vector has to be perpendicular to the magnetic vector. That force vector is not just pointing that way, it's pointing in the reverse direction of where the electron came from. So as this enters that region, the translational velocity goes to 0 and it is reversed. And that's how that mirror point occurs. Now, I'm going to do an analogy here. Again, I'm dwelling a little bit, perhaps too long on this, but this might be helpful. This is a completely different thing. It is not electromagnetic, but it has a rule. It says the tape has to be flat against this cylindrical dowel. That's uniform cross-section, same diameter here as here. So all I'm going to do is make sure the tape is pressed against the wood. I am not going to direct what the tape does. So let's just turn this like that. And you can see that we're getting a spiral. Okay? Like with the uniform magnetic field. Let's do the same thing with a dowel that is tapered. This is a smaller diameter than over here. Not much, just a little bit. So let's do the same thing here. I'm just going to press my finger so that it will stick to the wood, but I won't direct it. It's just following its own path. So we'll just keep going. You notice it's starting to go back on itself? Okay? Just a mechanical analogy. So here's a little globe. Now when you go on the internet and you type in Earth's magnetic field and hit images, you'll get all kinds of drawings. And here's a typical thing you might see. Now the S here is the magnetic pole. This is a south magnetic pole at the north geographic pole. We talked about that in an earlier session. And we have a north magnetic pole at the south geographic pole. Nice drawing, nice uniform, even pretty, I might say. But there's something wrong with it. You know what's wrong with it? All of the lines of force go to the poles. It's as if there's a giant bar magnet in here with the poles near the geographic poles. That's really not the way the Earth's magnetic field looks, though, if we could see it. And here's the reason. So here's a cross-section of the Earth's magnetic field. The orange represents the solid mantle. The yellow is a liquid outer core of nickel and iron. And the red is mostly iron. And it's liquid as well. I mean, it's hotter than the outer core, but because it has so much pressure on it, it doesn't act like a liquid. But our main interest is in the yellow. That's where all the electrical currents are that produce the magnetic field. Okay? That's the source of the Earth's magnetic field, not the poles. So here is, let's get this around here. This is a more realistic pattern. And if you look carefully, you'll see that the lines of force are not going to the poles. They're all heading for the inner core, or the outer core. These lines head for the outer core. These head for the outer core. Because that's where the electrical currents are that produce the Earth's magnetic field. Again, this is a south magnetic pole at the north geographic pole. So let's model that, okay? Let's model that. Now, I'm not going to build you a spherical core of molten iron. That's a little tricky. So we're going to have a much simpler model. It's a coil of magnet wire. Let's zoom in on that a little bit. You can see the individual windings, the individual wires. It's just magnet wire, lots of it. Let me zoom back out here. A little more. Okay. This is much more orderly than the sphere, okay? Think about our atmosphere or the ocean. We kind of know what it's going to do, but on a day-to-day basis, it's swirling and changing all the time. Now, because this is liquid metal, it's not as quick, but the processes are still there. The churning and the moving, and the electrical currents are constantly changing. We'll touch on that in just a moment. This is very structured, very simple, pretty much fixed electromagnet. To see how our field looks, we're going to try to duplicate what I've drawn, and we'll use these compasses. Notice they're almost all pointing north. There's a couple here that don't sometimes, and I'm not sure if they got reversed in polarity or I've got some of the struts under the table actually exhibit a magnetic effect. So we won't worry about them. Now this is not on yet. So we're going to sprinkle these steel filings onto this sheet of paper. I'm going to take a few moments here to try to make it as uniform as possible. We'll get a better image that way. Okay. And now, let's power up. Over here, let's see if we got the best, we can come a little closer without losing anything. There we go. So notice that all of these north poles want to point to the south magnetic pole. Remember, and we have a south magnetic pole at the north geographic end of the planet. and we have a north magnetic pole at the south end. Although it's really not at the end now, you know it's in the core, and that's why these lines are pointing to here and not to there. Notice how the blues over here are pointing that way and the reds are here. You can see, if you track those, you can see lines appearing in your imagination. Now on this side, I need to tap this because there's a lot of friction. As they clump together, you can see lines appearing. And it pretty much matches some of what I've sketched on here, okay? I might zoom in a little for you so you get a little better view. Let's do this. There we go. You can see the lines forming, okay? Now, remember, the Earth's core is a liquid sphere. It's not a fixed electromagnet. And because of that constant swirling and changing and all that, the Earth's magnetic field flips. It has flipped 183 times in the last 83 million years. And its average is 300 to 400,000 years in each direction. That's just an average. The last time it flipped was over 700,000 years ago. It takes 7 to 10,000 years to flip, I guess. You might want to check me on that. I have trouble remembering some numbers. So we're going to reverse this just for fun. I won't take 10,000 years. I'll do it in 10 seconds here. And now all of the south poles are now pointing this way, and the north poles are in that direction. But we still have those lines of force. And I'm going to switch it back to the way it is today. Okay. Now the last thing I want to call to your attention is notice that here's the equator, here's the 45th parallel, and a lot of us live in this area here. And we're holding a compass. Our compass is pointing to the North Geographic Pole. But if you look at the magnetic field, you'll see it's pointing into the Earth. So let's see if you can see that. There we go. Okay. So the point I want to make is when you are walking around with a compass up here, most of the magnetic field is really down into the Earth, this component here. And just a little bit of it is actually pointing to the North Pole. That is what you're using on your compass. That is what the compass is responding to. Whereas most of the magnetic field up here is into the Earth. Okay? Well, I hope you've enjoyed this session, and I look forward to being with you in session 8. So take care. I'll see you later. Bye-bye.